Now we have the boundary layer set up, and in this part, we will start the simulation or iterations. But before that, we want to create a few quantities to be monitored because we are looking at the aerofoil. So we're interested in the lift coefficient and drag coefficient, or lift and drag. So in the reports, we want to create the CLCD. So we want the CLCD to be reported during the iterations or drag and lift. So let's see, how do we do this? I can do one. So right click reports and choose new report and choose the first flow and energy. We can do the lift force coefficient. It won't tell us to be lift or drag. We need to define later. So for force coefficient, and so first of all, we do, for example, a lift C. So let's say C lift. So that's a lift coefficient. And because it's lift, it's along the y-axis. So the second one should be 1. And we need to choose pressure and shear because we are simulating the viscous flow. The surface friction will also contribute to the lift because there is a vertical component. And we need to put in reference pressure, reference density, and a reference velocity. So we need to find all these 3 parameters. These are very important when we look at the coefficient. So for pressure, we can find it in here. So reference values, and we can see reference pressure. So this is value, and we can put it here. So reference pressure, so just copy in. Have reference pressure, reference density. Okay, for the air density, we can find on a gas. And if we open air, because at the beginning we choose constant density, so this is density of the air. And then we can go here and put the put the density in here. And reference velocity we know is 10 meters per second. And reference area is 1 meter square. And because the chord is 1 meter, the parts we need to select aerofoil because the integration will be over the aerofoil. Right, so it's finished for the lift, and we can copy and do a similar thing for the drag. So we name it C drag. It's basically similar, just change the coordinate from y-axis to x-axis. So this will be the drag coefficient. If we click both, right click, and then create a monitor in the plot from report. So if we want them to be plotted together, we can choose single plot, and they will be plotted, updated in here, lift and a drag coefficient. Okay, so also we want to monitor how the flow field evolves. We want to create a scalar field. So on the scenes, we want to introduce a scalar. So that's a scalar field. And we need to choose a part. Apparently it's a region, doesn't matter. And scalar field, we want to do velocity, x velocity. It will be this one. Okay, and now we are ready to go. And the first step is to do the initialization by clicking this red flag. So you can see the entire flow field will be initialized as 10 meters per second. Now we can click this little person to run. And this is the evolution of the residues for each equation. And this is a scalar field. We can see how the flow evolves. And we can also change how the contour is represented. If we go to scalar and field, or choose smooth. So this is a smoother contour. See the evolution of the velocity field while it's progressing. And also we can see the drag and the lift coefficient, and they are also reported in here. Okay, so if we see the drag, lift, although these are all activated earlier, but doesn't matter. So this is a drag coefficient, this is a lift coefficient. And drag is very small, and lift is about 1 magnitude higher than a drag. So there's more lift. And you can see they are almost flat. Okay, so by default, this simulation will continue for 1000 steps. And this is a residue. You can see the top two curves are already below 1 to the power of -5. It's very small residues. And we can consider this simulation is converged. So this is the fourth part to show you how to do the initialization and the iteration, and also more importantly, how to create CL and CD.